My example of a joint variation is a mechanical engineering problem or relationship. The power that a shaft can transmit varies jointly to the rotational speed and to the cube of the diameter. If a shaft can transmit 50 horsepower with a diameter of 1.5 inches at 400 RPM, what diameter is needed to transmit 120 horsepower at 900 RPM? All right, so you can imagine the automakers have engineers who are familiar with these things. Some of us have cars where if you exceed a certain speed, it goes into the red zone on the speedometer, and that's a point where your engine may just break down. It may just spin so fast that something's going to break. And one thing you can bend or break is a crankshaft. In fact, I think that happened to me years ago on a van I drove. And so it has to be strong enough to both spin fast enough and handle all that power, that torque that's being placed on it. You can imagine that race car drivers, the top race car driving teams have a mechanical engineer as a mechanic in there who knows about these things, and because sometimes they make these materials in their cars, and in order to keep the weight down, they choose special kinds of materials for certain purposes, and so you need to know how strong something can be so it won't break down. All right, so let's begin to translate this. The power, and my power is being measured in horsepower. In this case, I'm going to call that P. And horsepower is the English unit for power. I think in the metric system it is watts. And but anyway, power that a shaft can transmit varies jointly, and I'll explain that in a minute, to the rotational speed, and I'm going to call that R, and to the cube of the diameter. So again, don't overlook those key words here. I'm going to call this D to the third power, cube of the diameter. So these little details sink students on some of these problems if they read it too fast and don't pick up those words. All right, so varies jointly just means that we're comparing one quantity to a product of at least two other quantities. So we're just multiplying is all we're doing. So the power is being compared to the product of the rotational speed, R, and the cube of the diameter. And then to write our equation of variation, we bring in K, so P equals to K R D cubed. So there's our equation of variation for any of these types of problems. The rotational speed, by the way, I'm measuring in revolutions per minute, RPM. So that's what RPM is, revolutions per minute, or how many times it spins every minute. Okay, so now we can plug these numbers here in and find out what K is for this particular kind of material they're making this shaft out of. So P is 50. So 50 equals to K times R. R is R is revolutions, so that's 400 RPM. And then D, diameter, is 1.5 to the third power. So to solve for K, I'm going to need to divide both sides by this quantity here, 400, 1.5 cubed. And that solves for K. Now, I may have stumbled here and gotten some friendly numbers. Let's see what happens. I think that we can reduce this fraction real nicely. Ordinarily, I tend to just write the fraction out like this and finish the problem. I don't like going to decimals, and I'll tell you why, again, because when you go to decimals, you really need to use a lot of them. Probably all of them that show up on your calculator screen. If you round it off too short, then every time you round off a decimal number, you create an error. And those errors can really be magnified in some of these problems. For example, if the error is involving d cubed, then when you cube the error, then you get a much larger error. So I would discourage the use of decimals until you get to the very end of the problem and run everything through the calculator at the very end, and then round it off. But in this case, I think we could probably reduce this fraction somewhat. The 50 goes into 400 8 times, and something tells me 8 times 1.5 cubed is going to be a friendly number. Let's see, 1.5 raised to the third power times 8 is 27. So I got lucky, I just made up these numbers, but k is a rather friendly fraction here, just 1 over 27. So there's k. And now I'm going to replace it here with that number, and then we'll have our full equation of variation. So let's see, P is equal to R d cubed over 27. So this would describe this problem for, the type of material this drive shaft is made from. And if you change the material, then this wouldn't help you at all. You would have to recalculate k. So it only works for that particular kind of material.